deep surface physical properties of early galaxies and black holes.
All right, so thanks for coming back. Indeed, I will focus on the physical properties of the early galaxy around the ionization and beyond. It will be mostly based on, focused on JWST spectroscopy. We agreed with Rebecca that she would cover the photometric imaging part, and she did that extremely well yesterday. So this is, you barely see it, but this is the most distant galaxy put in the same scale as a local galaxy like the Milky Way. And this is essentially an embryo of one of these kind of galaxies, which will become a galaxy even more massive than the Milky Way. And it's always fascinating to think that this small, very extremely small thing will grow to become something like that across the 13 billion years, across the cosmic the goal of, one of the primary goals of JWST is to understand how these embryos came to be and how they managed to become these supermassive galaxies across the cosmic epochs. And the main finding is that these small things here, these small embryos, are not just scaled down versions in mass and size of local galaxies, are quite different. Indeed, there are several remarkable discoveries with JWST, many of them totally unexpected. One of these you have seen that discussed several times during these lectures, that early galaxies, many of early galaxies were too luminous too early. But there are also several other puzzling findings and exciting findings. That is, for instance, the quenched galaxies who have not been discussed much, but they've been found to be already passive very early, some of them in the universe, and seem to have formed too many stars too early, according to the star formation histories. The chemical enrichment is also puzzling in the sense that we find very enriched galaxies already within the first few 100 million years after the Big Bang, and with chemical enrichment which are really strange. And black holes are also one of the main puzzles that have been found by JWST, in the sense that many of them seem to be too massive too early, we'll see too naked, and also too weird. So Yohi, Rebecca, Pratica, and many others have discussed a lot. These I will not touch again because you already heard a lot about these. I will mostly focus on these other things, okay? Since my main goal is to highlight how different are early galaxies with respect to the local and how puzzling, I'm not always sure about your background. I will also briefly touch on what we know about these galaxies locally, and then see how the distant galaxies found by JWST differ. So sorry if often I will say things that for many of you are obvious, but just I think it's useful to have some refreshing concept. So we know that young galaxies are dominated by hot stars, which produce a lot of ionizing photons, and very blue. And as the galaxy stellar population ages, this fraction of ionizing photons just drops very quickly, and the galaxy becomes much redder, and you develop stellar features such as this prominent Balmer break. Remember this because it will be very important. And of course, these in young galaxies, this large amount of ionizing photons results in producing H2 regions where primarily hydrogen is being ionized by several other species, and you have a recombination equilibrium where the hydrogen atoms recombine, the electrons recombines with protons in some higher states, and then you have a cascade of transitions which produce these several emission lines depending on the matrix of transition. But the bottom line is that each of these lines is emitted, has an emissivity which is known to scale very well with density, with the square power of density. Remember this dependence on the square power, which is very important. This is a typical spectrum of a local individual H2 region with these strong recombination lines from hydrogen. And of course, you have in real galaxies, you see that these are actually combined with the continuum of the stellar populations, which again ages, as it ages, becomes more prominent with respect to the nebula lines. Now, this is a local star-forming galaxies, and this is a typical star-forming galaxy that we see with JWST, say, at the epoch of reionization. So now the emission lines are far stronger than with respect to the continuum that we see in local galaxies. And you see, I mean, here you see barely the continuum while the emission lines are extremely prominent. You see these even more strongly in these stacked spectra, which are in redshift beams. And again, the emission lines are so strong that they go out of scale, and the continuum you have to essentially stretch the flux axis to detect it, okay? And you want to quantify this prominence of the emission lines with respect to the continuum, and this is done with the well-known quantity that is equivalent with it, which essentially is the flux of the lines relative to the continuum. And what is found is essentially the equivalent width of these emission lines is orders of magnitude higher than seen in local galaxies. Local galaxies is a few angstrom, maybe 10, a few tens of magnitude. Here we are talking about thousands, okay? So it's really, really much higher. And of course, what is the interpretation of it? Okay, the emission line is essentially taking the processing component of the spectral energy distribution of galaxies. You have many more ionizing photons relative to the evolved. This is extremely young circulation. These are so extreme that simply invoking young ages is not enough. You have also to often invoke metal-poor stellar population because these are more effective in producing ionizing photons. Sometimes you have, as we heard, the need for the top-heavy initial mass function, and in some cases you also need the contribution of AGN. Keep in mind that the nebular emission lines, the nebular emission globally is so strong in these early galaxies that you see also in the continuum that is in this so-called Balmer jump, which is essentially the free-bound Balmer continuum, okay? So this is very rarely seen locally, but in distant galaxies we see more and more often. And the interesting thing is that, it means that most of the stellar continuum most of the continuum in some of these cases is not stellar, but is actually nebular. And an interesting other thing is that this Balmer continuum makes the spectrum redder. So the thing that very young galaxies should be extremely blue is actually wrong. Because of the strong contribution from the nebular continuum, it actually makes this become actually redder. Unless, of course, you have an extremely high escape fraction, in which case there is no recombination, and essentially you remove this nebular component, okay? The other, of course, we discussed the Balmer recombination lines, but you have a lot of other metal lines. What is the origin of these other lines? Okay, so you have not only recombination equilibrium, but you also have thermal equilibrium, which is in this system, and this is mostly governed by the metal collision excited lines. So in a simplified two levels atom, you have essentially that the upper level is populated by transition from the upper levels, for instance, by recombination. But then you have transitions. You have an equilibrium where this is, on the one hand, depopulated by spontaneous relativity transition, which is what we see through the emission lines, okay? And then you have collisional excitation, primarily with the electrons, typically, and collisional de-excitation, same typically with electrons, and then you have absorption and stimulated emission, okay? These components are ruled by the so-called, you may know, the Einstein coefficients, and the terms IA, which is the coefficients for spontaneous transition, is the inverse of it is essentially the lifetime of the level, okay? And for the so-called permitted lines, for permitted we mean permitted by dipole transition, this quantity is extremely high, which means that the lifetime of these levels is extremely short, of the order of 10 to the minus 8 seconds, okay? However, there are other lines which are forbidden by dipole transition, but they are still possible by quadrupole transition. And as a consequence, this coefficient is extremely small, which means that the lifetime of these levels is extremely long, okay, of the order of seconds or several hundreds of seconds. In this case, the electron stays on the upper level for a long time long enough that it can be collisionally de-excited and so potentially suppressed. So just to recap the terminology, just most of you are familiar with the permitted lines, quadrupole transition, which are essentially the forbidden lines, which are typically labeled with in square brackets, and then the semi-forbidden lines, which have this notation here, okay? Now, if you neglect absorption and stimulated emission, you can calculate the emissivity of the lines by the equilibrium of excitation and the excitations. I don't have time to go through it. I saw this on the blackboard. If you did, okay, good. So you know it's relatively simple to work it out. And you get that the emissivity is essentially given by this quantity here, where this is essentially the collisional excitation rate, and where we have introduced this quantity, which is the critical density, which is essentially the density above which the collisional excitation rate is higher than the radiative spontaneous transition rate. Okay, you have many more collisional excitation than radiative transitions. And in the low density limit, well below the critical density, the emissivity scales quadratically with the density, and in the high density limit instead scales only linearly. Okay, so what you have therefore is that in the low density limit you have this square dependence, and in the high density limit you have these above the critical density that the combination lines and permitted lines keep growing quadratically with density, while the forbidden collisionally excited lines essentially stop growing quadratically, and beyond the critical density only increase linearly. Okay. Now, this quadratic dependence is fundamental because it means that you can have a very small region with low mass, but if the density is high enough, can actually outshine much more massive regions which are low density because they essentially have lower density. Additionally, when you go to very high densities, it means that the forbidden lines become actually much fainter than the permitted lines and the recommendation lines. So keeping this in mind because this will be fundamental. So in the spectrum of star-forming regions, we have plenty of these collisional excited forbidden lines. And what kind of information do you infer from it? So you already, Laura already mentioned this. Essentially, the intensity of these transitions depends, this collisional excited transition depends on temperature and density. However, there are classes of these transitions which are predominantly dependent on temperature, particularly the so-called auroral lines, which are coming from different, relative to the other transitions, which are coming from states which have very different energy levels. So essentially, the excitation depends a lot on the temperature, which enables this high level to be populated, while transitions that comes from levels which have similar energies primarily depends on the density. Okay, well, depends very little on the temperature. Let's focus to begin with the these kind of transitions. And as Laura already showed yesterday, there are several of these doublets which are sensitive to density. This is, for instance, the classical oxygen 2 and sulfur 2 and so on. And they typically have this S-shaped dependence on the density. And this is pretty much obvious if you think about it, because in this low-density regime, you are in the case where both transitions depend quadratically on density. And then in the high-density regime, you have this regime where both transitions depends linearly on density, so they are essentially constant in these two regimes. And the regime where they are most sensitive, the ratio is most sensitive to the density, is in between the critical densities of the two transitions, okay? Which is different for different kinds of transitions. So you can have different doublets with different critical density where you can probe different density regimes, okay? Now, with JWST, we have now managed to measure these doublets, these density doublets, out to very high redshift. And therefore, this has been extremely useful to trace the evolution of the density of these ionized regions in galaxies. However, before we go into that, keep in mind that we are also, again, with Webb, capable of mapping in individual galaxies these doublet, and therefore measure the distribution of densities and temperatures and metallicity and so on. And for what concerns the density, you can see in this, for instance, in this case, that there is a lot of variation inside a galaxy in terms of density. So in this case, we estimate that there is a variation by essentially 1 order of magnitude in density of the gas across the galaxy, okay? So it's always, how to say, very simplifying to ascribe a single density to a galaxy. So keep this in mind, and we'll come back to this in a minute. So by measuring this doublet as a function of in multiple galaxies now with Webb out to essentially beyond the epoch of ionization, we see these trends where more distant galaxies actually are much more dense by actually even orders of 1 order of magnitude or more. This is actually this is based on a couple of doublets which are sensitive to this how to say density regime. But as I hinted, when you use other transitions, you are sensitive to a different density regime, and you see that you see still this increase in density, but you are probing a different phase, much denser than probed by this doublet. In this case, this carbon-3 doublet is sensitive to density up to a few times 10 to the 4. So there is this trend, but tracing different phases, and actually now people have used also ALMA to trace doublets in the far infrared, which instead are sensitive to much lower transitions. And they see that there is actually a broad range of transition, even in the same galaxies, okay? From 10 to the 2 up to 10 to the 4 particle per cubic centimeter. There is still this trend of increasing with redshift, but clearly these galaxies are very much stratified in density. So it's true that early galaxies are denser, and this is probably associated with the fact that they are very compact and in the early phases of their formation, but they have a very broad range of density in this. And you will see that this is actually associated not only to a density stratification, but is also reflect a chemical enrichment stratification. The other interesting finding of Webb is that the excitation constitution of this ionized region is extremely different from local galaxies. In local galaxies, you see, for instance, this oxygen 3 line, 577, which is doubly ionized oxygen, is about as strong as the oxygen 2 singly ionized oxygen line. And this is typically the case for most local galaxies. This died, okay. In the most distant galaxies, instead, you see that the oxygen 3 is much stronger, while the oxygen 2 is barely detected. Many times is actually undetected. And this is quantified more better in these diagrams. There are several of these studies where you have the oxygen 3 over oxygen 2 ratio as a function of equivalent width, which is, as we said, is also peculiar in high-redshift galaxies. And you see that this ratio in this distant galaxy at redshift around the ionization, epoch of ionization, is orders of magnitude higher than what we see locally. And this is highly informative. There are various interpretations for this. One is due probably to the much higher ionization parameter. The ionization parameter is a fundamental quantity in the theory of the modeling of the ionized regions, and it essentially is the ratio between density of ionizing photons impinging on a cloud relative to the gas density. Essentially, it's the number of ionizing photons per atom, okay? And you see that this ratio is strongly, the oxygen 3 over oxygen 2 is strongly dependent on the ionization parameter. The higher the ionization parameter, the more you produce highly ionized oxygen, okay? And this essentially is telling us, in this case, that in these galaxies, you have a much stronger ionizing field from young stars and probably metal-poor stars, combined with compact size makes this ionizing flux much denser, and this boosts the ionization parameter, makes the overall this photoionized region much more ionized than what we see locally. There are various other interpretations. For instance, again, very young stars and metal-poor stars, which tend to have harder ionizing spectrum, so we produce more oxygen 2 than oxygen 1. Also, as was mentioned by Laura yesterday, it's possible that these clouds are, because of the strong ionizing field, are actually matter-bound. You see, this is the ionization structure of a cloud, typically ionized by stars, where you have doubly ionized oxygen in the central region, and then you have this partially ionized region where you produce oxygen 2, singly ionized oxygen. If these clouds are cut, because essentially there is not enough matter, you get rid of the oxygen 2 region, and you only produce mostly oxygen 3. So this is a very exciting perspective, which is linked possibly to the escape fraction of ionizing photons, because the photons manage to escape the cloud. And then possibly there is also the contribution of AGNs, as we will see. Let's now move to the chemical enrichment, which was also mentioned here and there also by Laura yesterday. Just a reminder about definitions. You see the various ways to, quantify the metal enrichment in terms of mass of metals relative to the total mass of baryons, in terms of with the Z quantity, in terms of relative numerical abundances relative to the sun. And also you often use this notation here, typically where the element is A is oxygen, which is, you can ask me later why we use 12, but that's not important. Okay, so you know that metals are produced by nuclear fusion and other processes associated with stellar evolution inside stars and their explosive phenomena. And so metals produced are being recycled by subsequent generation of stars, of course, and so you expect that the metal content in galaxies increases with time. And so it provides a measure of the integrated star formation history, okay? But is much more deeply associated with the other properties of the galaxy, in particular with the mass of stars and the star formation rate. And you can understand this very simply with this simple cartoon. For instance, if you have a closed box, a single cloud that evolved as a closed box, with time the metallicity must increase, of course, because you produce more metals. But of course, the mass of metals relative to the mass of stars remains constant, because you produce as many metals in proportion to the mass of stars that you produce. And the star formation rate decreases because it's proportional to the mass of gas, and you are consuming it, and so you slowly decrease it, okay? If you have an inflow of pristine gas, then this dilutes the metallicity, so the denominator of the definition of metallicity. This doesn't affect the mass of metal relative to stars, because it's just hydrogen that is being poured in, and helium, while the star formation rates start to increase because you provide fuel for star formation. If you have an outflow, if you expel everything in the SM, both hydrogen and metals, the metallicity doesn't change. But if the outflow is metal loaded, then of course, because for instance produced by supernova, you decrease the metallicity, and you eject only metals, so you don't eject stars, so the metals to stars ratio decreases. And of course, removing fuel for star formation, you decrease the the mass of gas and therefore the star formation rate. So you see that you have to combine the metallicity with other information about the properties of galaxies to understand these various phenomena which we call the baryon cycle around galaxy and the environment, in which they evolve, okay? Now, most of the way to combine this information, the most important is probably combining with the stellar mass in what we know as the mass-metallicity relation. That is, more massive galaxies are more metal-rich. And this has been interpreted in various ways. One way is that more massive galaxies have a deeper potential well and therefore are more capable of retaining metals, while low-mass galaxies lose metals via outflows more easily. Another possibility is simply aging. That is, in more massive galaxies, you have had more time to produce more metals, and therefore that's why they are more metal-rich, okay? And another important relation is the so-called, is a secondary relation as a function, that is the dependence of metallicity on the star formation rate, actually inverse dependence, that is, at a given stellar mass, the metallicity is inversely proportional to the star formation rate. And so much of this dispersion that you see in the mass metallicity relation is due to this secondary relation. And you can see this better in this other projection of this diagram, where you have now the metallicity as a function of star formation rate in beams of stellar mass. And you see that at the given stellar mass, the metallicity decreases as a function of star formation rate. So this is actually, you can see this as a three-dimensional surface, okay, where the metallicity depends on both mass and star formation rate. And actually, you find that once you take into account for both these dependence, the dispersion of metallicity in this surface is extremely small, okay?
Is it a simulation?
No, there is no simulation here. These are all observations.
So,
These are just observational aspect, okay? So this is essentially, this small scatter is reflecting the fact that essentially, at least in the local universe, this metallicity is driven by a very smooth equilibrium between inflow, which dilutes, outflow with eject metal, and formation of stars in the star formation clouds that increases the metallicity. So there is a very smooth, how to say, equilibrium between and secular evolution about these quantities. Keep in mind that when you interpret this kind of correlation, as usual, that correlation is not causation. So it's very useful to find this correlation, but you have to go beyond and to understand what is causing them, okay? For instance, this inverse correlation between metallicity and star formation rate is, everyone, I think, agrees that is mostly driven by an indirect effect, that is, when you have an inflow pristine gas on a galaxy or a low metallicity gas, this dilutes the metallicity because it provides mostly hydrogen but not metals, and this decreases the metallicity. And on the other hand, the additional gas that is fuel for star formation boosts the star formation, so you have an increased star formation rate, and this results in this correlation. But to say more causal relation is actually the relation between gas inflow and metallicity, okay? Now, yeah. No, it is. In the full modeling, you have also the alpha and so on. But I think the main effect of this anti-correlation is mostly driven by the so overall, the metallicity is essentially tracing this baryon cycle between accretion, ejection, and recycling of gas. This is a cartoon, but as was discussed, this has been implemented in extensive simulations. This is a zoom-in simulation where you see on this side the metallicity of a John disk, and this is the radial velocity. You see these massive outflows, which are metal-loaded, and then inflow of gas, which is instead very low metallicity. And so you have this exciting baryon cycle. And So if you want to understand how this scaling relation and this barrier cycle was established across the cosmic epochs, you have to look at back into the past and see how in these various quantities, star formation, stellar mass, and chemical enrichment actually started and evolved across the cosmic epochs. So you need to go to look at this evolution of the chemical enrichment across the cosmic epoch. And the main point is how do you measure the metallicity, okay? This was hinted in the past lecture. Let me revise it a little bit more carefully to highlight the difficulty, how difficult is this. So you essentially take one of these metal lines, for instance, the oxygen 35W7, and the emissivity, therefore the flux of this line, we saw that this is a collisionally excited line, so we saw that in a few minutes ago, is given essentially by this equation that we have seen earlier, but essentially rewritten in terms of density and abundance of elements. And so this is, of course, depends on the amount of oxygen that you have in the ionized region. And so in principle, from the flux, you can derive the oxygen abundance and therefore the metallicity, because oxygen is the most abundant element in the ISM. However, the collision excitation rate strongly depends on temperature. So if you don't have a handle on temperature, you are completely clueless, okay? You have this critical dependence. So you have to measure the temperature, and that's where we use this transition that I mentioned that comes from highly excited labels, which are strongly dependent on temperature. And these are typically called auroral lines, okay? And the oxygen 4363 is the most famous. We have seen several times because it's typically the brightest. But there are several of them. You just can pick one of these. And the line relation of these auroral lines relative to their lower excitation transition of the same element is strongly dependent on temperature. So you can measure the temperature, which is typically for this star forming region, typically 10 to the 4, but it can change a lot depending on metallicity. Keep in mind, connected to a question that I heard yesterday, that the emissivity of these auroral lines also depend on density, okay? And I'm showing this as an example. This is exactly where you see the temperature as a function of density, and these lines are lines of constant ratio between the auroral lines and the lower energy transition oxygen 35W7. Okay? In the density regime, this ratio depends only on temperature, essentially, okay? And you can reach actually fairly high temperature, especially if you have AGNs. There is no problem about having a very high temperature until you get to the point where you ionize by because it's too hot, okay? But you see, when you go beyond the critical density of oxygen 3, W7, which is about 510 to the, 7 times to the 5, you start, while the auroral line has a much higher critical density, you start to suppress strongly this line, and you can have very high ratio, very strong auroral line relative to the oxygen 3, even at very low temperatures. So when you see extremely strong auroral lines, keep in mind, especially at this very high ratio where we do see this system that we've seen, which can be extremely dense, it may not be tracing high temperature, but actually, and therefore low metallicity, but actually may be tracing actually very high density. So be very careful when you again, with JWST we were exploring a totally uncharted territory before that, and therefore we are finding things that we were not expecting to find based on the local counterparts, okay? Now, the problem of these auroral lines is that, as you can see, are extremely faint. You see, you barely see it with respect to the H alpha and the oxygen 3 5W7, okay? So it's in the local universe, it is a lot difficult even in the local universe. Typically, we have a few hundred galaxies in the local universe, or H2 region where we can measure this line. And at high redshift, it was considered to be sort of nearly hopeless. And I remember conferences before the launch of the JWST where people were saying, OK, we will, maybe with Webb, thanks to its sensitivity, we will manage to measure the auroral line maybe up to redshift of 2, maybe 3. But reionization, redshift 6 or 7, totally impossible. Forget it. And the first spectrum that was released by Webb showed this beautiful, at redshift 8, this beautiful auroral line. So everyone was jaw-dropped, mind-blown, because we were not expecting this, okay? And the reason why you actually managed to see this actually now in several of these high-redshift galaxies is partly due to the JWST sensitivity, which actually is even better than we thought, than we expected. Partly because the gas is hotter, and because of the lower metallicity, and so this helps to boost the auroral line. And there are other aspects that I don't have time to discuss, but are very intriguing if you want to ask me later, okay? The point is that we now, with Webb, we detect dozens of these auroral lines in distant galaxies. Still are not enough to do an unbiased census of metallicities measurement. High redshift, we still have to rely on stronger lines, the so-called strong line method, that is where we take the ratio of these, some of these strong lines and calibrate it with the direct method of the metallicity. But the good thing is that with these detections of the auroral lines at high redshift, we can produce this calibration in the early universe. And this was a big if, because it was not obvious that we could use the local calibrations at high redshift. So this has been a big leap forward. So with these calibrations now, everything more careful, we could now explore, for instance, the mass material relation. And this is one of the several versions of several studies that has been obtained. There are several references there. And you see that, as Laura was mentioning yesterday, with respect to the local relation, we have, of course, at the given stellar mass, the metallicity is lower. This is not totally unexpected. The main takeaway of this is that already at these early epochs, we already have a mass material relation, although much flatter than locally. And this is informative of simulations and models. The other important takeaway point, we are going up to redshift 10 here, that already these galaxies, within the first few 100 million years.
Sorry, here you show local and redshift 2 to 10.
Yeah.
Is there any smooth evolution?
Yes, sort of. This is, sorry, these are redshift 2 and 3, so you still see. Okay, yeah. And the other point is that the chemical, we are talking about galaxies here within the first few, less than a billion years after the Big Bang, and these have already achieved about 10% of the local chemical enrichment. So chemical enrichment happened very quickly. And the other point is that you see the scatter here is much larger than in the local relation, which means that this process of inflows, outflows is no longer much in equilibrium. Probably there is a lot of more stochasticity in this effect in boosting the metallicity through bar-to-star formation and removing metal and diluting. So it's much more, of course, complex to model this in terms of simulation. But it's actually, there are models which manage to reproduce these properties in many aspects. If you take the most distant galaxies, we are now actually about 300 million years after the Big Bang, probably 100 million years after the onset of star formation, something like that. These actually have reached the metallicity already about 10% solar. And this is still, again, remarkable. Again, within a matter of an eye blink, you manage to boost this galaxy to a metallicity which is actually a remarkable fraction of the local solar metallicity. So it's, again, I know that Rita Andrea managed to do this. Well done. Yes?
Can I just quickly ask on this spot? So are these measurements of mass metallicity relation with the James Webb consistent, at least with the previous high redshift measurements like Manucci et al.?
High redshift, I'm coming to that. Well, the previous measurements were all less than redshift 3. And yes, those are more or less confirmed. There was not Yeah, this is essentially the previous measurement here, okay? So, but it's remarkable that in an eye blink, yeah.
So this discovery of early high metallicity enrichments, is it supposed to, or is changing the evaluation of primordial metallicities?
High, sorry?
You said that when discovered that there was a high metallicity earlier, right?
Mm-hmm.
So is it changing the picture of the observation of the primordial metallicities that are used in Big Bang nucleosynthesis?
No. I think the primordial, you mean Big Bang nucleosynthesis? No, I don't think that's, you don't go that far. No. I mean, it's surprising, but you can boost star formation to actually, in the end, when you trigger star formation, the chemical enrichment can actually, go up very, very quickly. Yeah.
Maybe you can just answer this question, but to reach too early compared to what?
To the age of the universe. So essentially here you are 2% of the age of the universe, or actually 1%, I think, 1% of the age of the universe, but you have already reached 10% of the local region. So the process, just empirically, the process of chemical enrichment just skyrockets in the first 100 million years, and then takes 13 billion years to arrive to the local universe. Just how to say, in terms of time scales. Then in terms of modeling, is challenging, but there are various models that can do that, okay? Then in terms of, we saw the fundamental metallicity relation, so now we are throwing in also star formation rates, so correlation between metallicity, stellar mass, and star formation rates. And so what you see here is the deviation between these three-dimensional surface that I showed you in a few minutes ago, okay? And up to redshift of about 3, there is no essential deviation. This was a remarkable result already in the past 10, 20 years, okay? No, 10 years, I think. So that is, despite that we are going very back in time, so here we are 90% of the age of the universe, galaxies, yes, evolve in mass, star formation rate, and metallicity, but they surf along this three-dimensional surface, meaning that they still comply to this smooth equilibrium in terms of accretion, dilution by metals, ejection of metals through outsource, and star formation rate. So there is still these, they're still compliant with this smooth equilibrium between these baryonic cycle and star formation. As you go to higher redshift, you see you start to deviate, and becomes, from this relation, becomes actually more metal poor. And the probable interpretation of this is that in these small galaxies in the very early universe, these are actually dumped with a lot of gas from the intergalactic medium, and they don't have the time to cope with this massive inflow to reprocess this gas into metals, and essentially they get simply diluted and they go below the relation. Okay, so it means that we are out of the baryonic cycle equilibrium, and the baryonic cycle equilibrium settles only at later epochs. This another point that again has for the densities. Keep in mind that, however, all of these galaxies do not have a single metallicity measurement; they have gradients. Okay, in the local universe, galaxies are known to have very smooth, relatively smooth metallicity gradients, where you have higher metallicity in the center and the lower metallicity in the outer regions. Okay, at high redshift is much more complex. When we manage to map the metallicities in a number of these galaxies, and they are much more irregular with the clumps of low metallicity stuff coming in. And much more irregularly distributed, which reflects this chaotic behavior in terms of accretion, mass outflows, and metal production. However, if you now try to azimutally average, as done in this work here, and to anyhow derive an average radial gradient, what you have here is this plot which is being assembled by Maria Kohler here, where in the local universe you have these negative inverted gradients, okay? And as you go to earlier cosmic epochs, these actually tend to flatten a lot, become essentially consistent with 0. And in the very early universe, okay, well beyond the reionization, you have a mass, all kind of scatter from very positive to very negative gradients. And you can interpret this in various ways through simulations, but the basic interpretation is that when you have a negative gradient, is simply tracing inside-out formation of the galaxies, where you first form metals in the center and the outer parts lag behind. When you have flat gradients, this is probably a consequence of stirring and redistribution of metals because of merging or because of outflows, and this can explain these, how to say, very flat gradients across most of the high-redshift galaxies. And positive inverted gradients are often the interpretation as the dilution of gas which is being dumped in the central gravitational potential well of these galaxies and strongly diluting the central region. So this is very highly informative, again, of the baryon cycle on resolved scales. And then I just want to finish this part of the global metallicity about, as Laura already mentioned yesterday, the search of very metal-poor galaxies, possibly aiming at population 3. The main focus here, again, I mentioned that most of the galaxies have reached already 10% solar. However, there is a growing number of the results, including from our team, where people are finding strong Balmer lines and extremely weak or even absent oxygen tree lines. And this is one of the most remarkable. Again, we are not a super high redshift, but around the epoch of ionization. And so now there is a growing number of galaxies that are low mass and low metallicity. Now we are talking about less than 1% of solar. And these could be candidates for population 3. I think there is still not, how to say, any smoking gun that these are actually POP3, but are going that direction. So there is a lot of excitement and push for going to explore more of these galaxies, and I'm sure that next week there will be a lot of proposals to follow up on many of these candidates. Let me, I so far discussed global metallicity. How am I doing?
25 minutes.
Okay, I'll probably have to skip that. Relative chemical abundances. So far I've discussed global metallicities, okay? But actually, different chemical elements are produced on different timescales. So massive stars produce mostly alpha elements, including oxygen, on very short timescales, okay? While intermediate mass stars then produce most of the carbon and nitrogen on timescales of typically a few 100 million years. And then iron is mostly produced by type 1a supernovae with a time delay of, again, 100 million years or typically a giga-year. And this is affect most of the iron peak elements, okay? So this is a cartoon showing that when you start a formation, the oxygen, the first element that you produce, and then through the injection of lower mass stars, you produce carbon, nitrogen, and then iron, okay? And this illustrates this more quantitatively. This is nitrogen over oxygen as a function of metallicity, which you can take now as a time axis, and carbon over oxygen over metallicity. And these are observations and models. And essentially what you see here is the initial phase of production, which is produced by the yields of core collapse supernovae, and then you have the production of intermediate mass stars. Many of the galaxies that we see at high redshift comply with this, but Webb is finding also a remarkable population of weird objects, and particularly systems which are, despite being very low metallicity, have very high nitrogen enrichment, okay? You see this, even the most distant galaxy known have this strong nitrogen emission. And this is sort of passing. There have been multiple proposals to explain this, from very massive stars, Wolf-Rayet, first generation of AGBs, feedback crystal formation, double burst, differential outflows. I don't have time to go through them. I just want to show empirically that some interesting results. So this is, again, the same diagram, nitrogen over oxygen is a function of metallicity. You see the local galaxies, and this is the distribution of stars in the Milky Way. And this is a collection of these nitrogen-rich galaxies found in the early universe by Webb, way above this local relation, okay? And interestingly, to begin with, you see some of the galaxies we can measure the nitrogen enrichment on different scales. This is the measurement for low density tracers, and this is for high density tracers. And you see that essentially there is essentially stratification not only in terms of density, but also in terms of chemistry. This extremely high nitrogen enrichment is only associated with the high density part of the galaxy, okay? So there is a lot of chemical stratification in these systems. The other result is that, okay, when you show the distribution of stars in globular clusters in the galaxy, actually, they overlap very much with these systems. So what we may be seeing in this system, regardless of what is the origin of the nitrogen production, is that we are seeing probably the formation of dense protoglobular clusters, which will not, we are not probably tracing the formation of globular clusters in the Milky Way because these are actually in the core of galaxies. They will merge to form galaxy cores, but we actually may be witnessing the formation of these very dense globular clusters in core of galaxies that will merge.
Why you form more nitrogen in globular cluster-like environment?
Yeah, this is a very open problem, and essentially it goes back to these several possible explanations. Okay, this is I think it's all these options are still on the table, and whoever you talk, you will give a stronger pitch on one of them, but I think they are still very much possible. Okay. Carbon is also supposed to lag behind oxygen, and this is the case for most of the galaxies that you see, to the point that we do not expect to see any carbon emission in these distant galaxies. But there are some remarkable cases where we see these strong carbon lines, which we were not expecting to see at all. And the inferred carbon abundance is actually supersolar, despite this being actually very low metallicity. These are located in this region of the diagram, okay, which are totally unpopulated by local systems, but interestingly are consistent with the so-called carbon-enhanced microstars in the galactic halo. So we will be seeing the formation of this particular star in the halo. And the only kind of, so you see that the population 2 core collapse patterns are totally inconsistent with this measurement. The only kind of yields that can reproduce this weird carbon enhancement are those from some classes of population 3 stars. In particular, the population 3, which explode through low-energy supernovae, are expected to produce much more carbon than oxygen. So this may be that we are seeing the fingerprint, the chemical fingerprint of the first generation of stars. This is, again, a very exciting area where people are working a lot, both with observation and simulation. Let me, in the last 20 minutes, discuss about the black holes. Marta will discuss this theoretically much more tomorrow or this afternoon, I don't know. Just again, to recap, I think I don't have to convince you that in the local universe we see a lot of supermassive black holes, including the Milky Way, and the mass of these black holes correlate with the mass of the spheroidal component of the galaxy. Typically is about 1% of the stellar mass, and there is this also strong correlation between black hole mass and velocity dispersion. And of course, although we detected these black holes dynamically in a few local galaxies, most of these black holes are seen when they're accreting through the glow of the accretion disks and the surrounding ionized gas, okay? I don't have to recall the Eddington limit. I hope that this is well known to everyone. That is when you essentially the limit where radiation pressure overcome gravitational pull. And then the spectral energy distribution of AGN in the local universe, at least up to relatively high redshift, is typically characterized by this strong Rule bump, which is produced by the accretion disks and produce a lot of ionizing photons. And we also have this very strong X-ray tail, which we thought was produced by this corona surrounding the disk, which produced X-rays. And this radiation, nuclear radiation, is then ionizing the surrounding a medium, and we typically see two main regions of ionized gas. This is called the northern region, which have relatively low velocity dispersion, standard and medium densities, and the broadline region, which is only seen in permitted lines, which have very high velocity dispersion, probably in the sphere of influence of a black hole, very small sizes, and extremely high densities, above 10 to the 9, okay? And this is why we don't see these in the forbidden lines, because it's well above their critical density. And this is why, despite being extremely low mass, is about a few solar masses only, it outshines totally the other nebulous lines which are coming from a more massive galaxy, just because the density is so high that it boosts the emissivity by a huge factor, okay? Okay, so standard scenario that how do you manage to make this supermassive black hole? I just mentioned it, but Marta will show you that it's totally untenable, that you produce a stellar remnant, and then you accrete it via up to Eddington to make it a supermassive black hole. Now, if you want to test these, you want to look again back in time and see how these black holes were actually made and assembled. And JWST now has discovered a plethora of these accreting black holes in the early universe. This is one of the, I mean, in image they don't appear particularly compelling, but the spectra are fabulous, fantastic with these broad lines, again, coming from the broadline region, these high ionization lines from the northern region, and we are seeing several of them, and these are just totally outdated collection of several of them out to redshift well beyond reionization. Again, we see these broad lines of the Balmer lines, which don't have a counterpart in the forbidden lines. And we are essentially exploring with Webb a parameter space which was totally unexplored with previous ground-based surveys, in particularly low luminosity AGNs, and going also out to higher redshift, okay? And what do we learn? Well, to begin with, there are a lot of them. This is the luminosity function of AGNs at redshift around 4 to 7. And there are one or two orders of magnitude in number and density above the extrapolation of luminous quasars. So this seems to be a different population. It's not just the continuation of the luminous quasar populations. There are so many that there are models that, as Laura mentioned, that claim that they could contribute to reionization, but I will not go into there. The other aspect is that, of course, you can measure, have a hint of the black hole masses, because the broadening of this emission here is thought to be primarily due to motion around the black hole. And if you know the size of this broadline region, which is locally is known to scale as the square root of the luminosity, you can get a clue on the black hole mass by combining the luminosity and the velocity dispersion of these lines. And there are equations that are called virial relations to derive black hole masses from these quantities. Once you use that, this is a sort of an outdated census of black holes found by JWST in the diagram where I showed the luminosity relative to the Eddington as a function of black hole mass. And you see that with Webb, we are now, these are the quasars that were known before JWST. With Webb, we are probing much lower black hole masses and also probing the dormant counterpart of quasars. So it's very exciting. It's a completely different regime with respect to what we were seeing before JWST. Marta will discuss this much more in detail, but if you take the most distant of these black holes, you run into the problem that these are already too massive, too early, okay? In the sense that if you assume the standard scenario where they have been constantly accreting at the Eddington limit, you actually can't explain them in terms of being seeded by standard stellar remnants accreting at the Eddington limit. So people, again, this will be discussed much more in detail by Marta, have developed alternative models such as the fact that the black holes may have born big, such as direct collapse black holes, or formed by runaway merging of dense nuclear star clusters, and we have seen that we see these dense nuclear star clusters, or from even light seeds, but that these actually somehow manage to overcome the editorial limit in short bursts of very high accretion. And in this case, when you use these models, you can somehow account for many of these, but so you manage that point to reproduce some of these black holes. But again, this will be discussed more in detail by Marta. There are also other peculiar properties of these early black holes. One of these is when you explore the black hole mass as a function of stellar masses, and the vast majority of them seems to be highly overmassive relative to the local relation. In the local universe, you recall that black holes are about 10 times less massive, 1,000 times less massive than the host galaxy, while these black holes are orders of magnitude more massive. Some of them are nearly as massive as their host galaxy, okay? Now, one should be cautious about interpreting this finding because there are a lot of selection effect involved here, in the sense that even if you have a broad distribution, because more massive black holes tend to be more luminous when they accrete close to Eddington, they are easier to detect. So there are a lot of selection effect in place, okay? However, even taking that into account, it's still remarkable, as Yoki was saying, that even if we are seeing only a tail of the distribution, that is remarkable that we are finding black holes that are nearly as massive as the host galaxy. Because this means that somehow the universe managed to create these monsters in these tiny galaxies. So this is highly informative of the seeding and the growth of black holes in the early universe. And as Yoki was saying, this is extremely challenging to produce, even if this is only a small population of the whole distribution. When you plot them on the black hole sigma relation, they seem to be much more aligned. Okay, so it seems that the black hole sigma relation is more is more fundamental, universal. Okay. Now, since sigma is somehow connected with the dynamical mass, if you combine this with the previous result of the offset on the black hole stellar relation, this may indicate that the baryons are already there, but somehow, and this explains this relation, but somehow they are prevented to form stars by some feedback effect. And so the conversion of baryons into stars, lags behind. Or another possibility that has been proposed by some recent studies that at low mass regime, most of these systems are totally dark matter dominated, so that's why they comply to the black hole sigma, but the stellar component is still lagging behind. The other interesting aspect is the X-ray weakness. Most of these JWST discovered agents are not detecting the X-rays, and this is highly significant. You see, this is the relation between volumetric and X-ray luminosity in local AGNs, and this are the AGN found by JWST, and they are orders of magnitude fainter than local AGNs. Okay, and this is regardless of the selection. It can be selection criteria. It can be type 1, type 2. Infrared select, so it's common properties at these early epochs of these AGNs. And there are two possibilities primarily to interpret this weakness. One is absorption. If you have extremely high column density along the line of sight, for instance, in the case of the broodline clouds, you can completely absorb the X-rays, and if these clouds are dust-free, as within the sublimation, dust-sublimation radius, you do not absorb anything else, okay? The other possibility is that these are intrinsically X-ray weak. For some reason, they miss this tail, this corona, and this is the class of models is in the framework of the so-called super-Eddington accretion, in which case you don't have this X-ray bump, but actually you go down very steeply in the X-ray emission. And so there is probably both scenarios actually applies. For what concerns absorption, another really mind-blowing result has been the finding that many of these, a good fraction of these AGNs show this absorption of the Balmer lines of H alpha. And I don't know if you appreciate how remarkable it is. It's totally mind-blowing because H alpha is not coming from the fundamental level. It's not a resonant line, okay? It's coming from n equal 2. So in order to have H alpha, H beta in absorption, you need to populate n equal 2. But n equal 2 is very short-lived, less than 10 to the minus 4 seconds. So in order to have absorption, you have not only to populate this, but to keep it populated. And the only way to do this is with large densities and large column density. In particular, we have found that you must have density higher than 10 to the 9 particles per cubic centimeter, which are essentially the densities of the clouds in the broadline region or the surrounding, okay? So the same gas which is absorbing the H alpha may actually be responsible for the absorption of the X-rays. And this is somehow linked to the population of the famous little red dots. Well, first there is a misconception that all AGNs found by JWST are little red dots, which is totally wrong. Okay, most of them are not little red dots. But about 10 to 30% are these little red dots that is this very compact and object with this red slope. These typically have this V-shaped continuum, blue in the UV and red in the optical, and typically have this prominent Balmer break. Now, this Balmer break, as I discussed at the beginning of the lecture, is typically ascribed to evolved stellar population, okay? And this was the initial interpretation for these little red dots. Evolved stellar population, but this Balmer break is so prominent that it has two implications, that the masses that you derive are extremely high, and as Yoko was mentioning, this implies that these objects are so massive that are cosmology breaking. You don't have a way to produce them, even if you convert all baryons in stars very early by the cosmic ionization. The other aspect is that since they are extremely compact, the implied stellar densities are huge. Essentially, you have the same stellar density as in the nuclear star cluster of the Milky Way, but orders of magnitude more massive than the Milky Way. Okay, so it's really puzzling and exciting and challenging. However, this is we have realized that this is probably connected with the H alpha absorption that we see, because when you populate the n equal 2, you can produce H alpha in absorption, H beta in absorption, and it doesn't stop there. You can produce H gamma, H delta, and so on, all the way to the Balmer break. So it's simply physics, okay? You don't have to do any modeling. Simply pure atomic physics that this absorption in the Balmer lines must produce a Balmer break. But this doesn't have anything to do with stars. It's just due to gas absorption, okay? And this was a model until last year. And then we tested this on this first object. This is a prototypical little red dot. And with a program, large program that we called Black Thunder, is we talked about acronyms at the restaurant a few nights ago, and I think this is fantastic, PI'd by me and Hannah Wubler. We detect in these objects the prominent H alpha absorption. And from this H alpha absorption, you predict exactly the shape of the Balmer break that you observe, okay? So it's fully consistent with this picture. Additionally, you can, from the narrow component, you can measure the dynamical mass of the host galaxy, which is an order of magnitude smaller than the stellar mass that you would infer if you interpret this Balmer break as stellar. So this Balmer break is totally gas associated with gas. So the non-stellar origin of this Balmer break relaxes a lot of this tension with cosmology and with extremely compact sizes. And then people have found a even more prominent Balmer break. This is way above what you can achieve with stellar atmospheres, and to the point that they have gone beyond of postulating actually a black hole embedded these thick atmospheres which produce these strong Balmer breaks. I shall mention that there's been also models which have proposed that there is not only a neutral envelope, but actually also an ionized envelope, which can produce electron scattering and produce these broad wings of the Balmer lines. And in this case, they claim that the bulk of the broadening is not due to the intrinsic BLR, but to this electron scattering, in which case the black hole masses that you infer from this broadening is not actually associated with the black hole mass, and therefore you are actually overestimating the black hole mass by 1 or 2 orders of magnitude, okay? And this may help to reconcile these relations. However, this has been debated by other works, so it's still been, because in terms of profiles not matching the prediction and also energetics. But in this context, so there is now a lot of debate on how we measure these black hole masses in this early system. And I think a breakthrough has been, again, this result on this prototypical elliptical red dot at Redshift 7, which is strongly lensed. And here we managed to resolve the sphere of influence of the black hole, so to measure the rotation field around the black hole, which turned to be perfectly Keplerian, okay? And so you can measure directly the black hole mass dynamically without doing any assumption. And this, interestingly, is fully consistent with the virial relation and seems inconsistent with the scattering scenario. So at least for a number of these objects, this seems that the virial relations still are a good approximation of black hole mass. The other interesting thing is that this Keplerian rotation curve is just purely Keplerian. It doesn't have any scope for a host galaxy, okay? So we can put very tight upper limits on the stellar mass from the dynamical mass. And it turns out that the black hole is essentially more massive than its host galaxy. If there is a host galaxy at all, because we don't see any host galaxy, okay? It's a sort of a nearly naked black holes. And this is extremely exciting because it means that it's a paradigm shift, because typically we think of galaxies forming and then the black hole being seeded in galaxies and then growing inside galaxies. It seems that in this case, the black holes just form before these galaxies, and then the galaxy will probably form around it. So there is a lot of excitement around this result. Let me mention 2 last points. That with Webb, we are also finding a number of dual AGNs that is separated, in this case, by scales of a few kiloparsecs. And so this is extremely exciting because the number of these dual AGNs is much higher than expected by the simulation. And so it's suggesting that merging may actually be more common. And indeed, we are now finding a number of black holes by these resolved offset BLR in systems, which are separated from scales of a kiloparsec down to a few hundred parsecs. In this case, there are actually 3 black holes in these systems. And this is extremely interesting because we find quite a few of them, and indicating that probably the merging of black holes, rapid merging of black holes in the early universe, may be an additional route for the early formation of black holes. And this has, of course, important implications for the gravitational waves that we expect from the early universe, especially in view of LISA. And this, I think, will be discussed in greater details by Marta. I think I will stop here. I was supposed to discuss other things, but I think I will stop here.
Thank you very much. We have at least more than 10 minutes to questions, so please, questions for Roberto. Yes, Sasha.
Yes, when you were talking about black hole mass measurements, and you have already mentioned that it's possible that with the black hole mass measurements, it can be 1 to 2 decks lower unless you are doing a proper dynamical mass measurement through lensing effects. You also spoke about the scaling relationships with the radius of the black hole with respect to the luminosity, and those have been constrained based on local aging population. So how relevant it is to apply them to redshift cases as well?
This radius of the BLR has been now measured with the gravity interferometry up to relatively high redshift, 2 to 4. And there is a flattening of the relation, so it doesn't scale any longer as the square root of the luminosity. But this is actually not too surprising because already locally we knew that when you go to the very high Eddington or super Eddington regime, the black hole, the BLR size is actually smaller than the extrapolation of the local relation. So one has indeed to correct for this, offset when measuring the black hole masses through classical virial relations. Yeah.
Actually, a similar question, but on the stellar mass. Can you comment more on how the stellar mass is determined? Because I think there could be similar effects.
In the black hole host galaxy, in the Aegean host galaxy. Yes, that's a very problematic thing in the sense that there have been various ways to do it by combined modeling of both the Aegean light and the stellar light, resolving with imaging in the host galaxies in very high resolution observation with NIRCam. Let's say in the end we have compared the various methodology, and all of them give essentially a similar result. Let's say in order to make these things compliant with the local relation, you would have to hide 2 orders of magnitude of stellar mass, which is very difficult. You would see these things that are 2 orders of magnitude more massive in these host galaxies. The other thing is that the finding that this Balmer break, many of these measurements were done when they were assuming that the Balmer break was stellar. Okay. Now that we are finding that in many of these systems, the Balmer break is not stellar, actually make the stellar masses even lower. So it makes the problem even more serious. And this seems to be applying to a large fraction of this system. So if anything, the uncertainty in the stellar masses now is actually pushing them to even lower masses. Yeah.
Tough problem. Question.
This is like way back early in the slides, but I noticed that the density inferred for GNZ11, like the electron density, had huge scatter on it, and I was just curious what aspect of the spectrum could create a huge scatter in your inferred density. Is it like blending, or is it something else?
This was measured with the a first attempt to resolve with constraints on the carbon-3 doublet, which was with medium resolution. So the doublet is very close, so it's very difficult at medium resolution to resolve it. Now we have a much deeper and higher resolution spectrum where we can actually resolve the doublet, and this is helping a lot. But we know that, again, many of these lines are actually tracing different densities. For instance, there is another doublet of the nitrogen-4, which gives densities which are way higher than, and nitrogen-3 way higher than 10 to the 9. And we think that in that case, those lines actually are coming from the BLR because the densities are far too high to be associated with the ISM. So there is a stratification. When you ask about the density of an object, is often not an obvious question to answer because you have different components, different traces, which give completely different densities.
Yes. At the beginning, you said that we are finding that high-redshift galaxies have higher densities, but isn't that expected given the density evolution with redshift?
Yes, that's what I was saying. It's not maybe too surprising. What may be is surprising that in some of these cases, these systems are more compact in the early universe, so certainly are expected to be more dense, but in some of these systems we are seeing densities which are going above 10 to the 6, 10 to the 7 for a large fraction of the galaxy, and in these cases they start to be, quite interesting because are really going into a regime that was not seen locally. Well, it's seen in molecular clouds, but not in the ionized phase.
Could it be that in fact it's a bias that you're just measuring the density where you see these lines? And so
Yeah, absolutely. But again, it's interesting that it's there. This component is there.
This is a provocative question. Pre-James Webb, we used to think that the high redshift universe of the time was quite different from
James Webb, it turned out that the universe at that redshift is actually relatively similar to the low redshift universe. But now we find that very high redshift is very different. So how do we convince ourselves we're not repeating the mistake of selection bias?
No, but that's cool. Certainly there are selection biases, as mentioned. And I started my lecture saying that these are all puzzling. It's not that we are settling and understanding all of this. So there will be a lot of more to observations and modeling to be done to understand this. But the bias, again, I'm always in agreement with the fact that it's important. But it's still also important that even if you find you find a tail, and that tail is extremely challenging to understand, that's still informative. Again, these, as I mentioned, talking about black holes is probably a tail of a broader distribution. But the simple finding of these absurd systems is telling us something about the way these black holes formed and so on. The same for the early chemical enrichment. So it's, same story for the chemical enrichment. When these, where was it? Sorry, long way ago. These an extremely highly, oh dear, there are a lot of slides. Yeah, okay. So this object here, with extremely high nitrogen enrichment, is a tail, again. The bulk of, this is a selection of these nitrogen-enhanced objects. The bulk of galaxies that we see with JWST are actually compliant with the local relation, okay? But the fact that these exist is still, even if it is a tail, is still highly informative because you have to explain how these systems managed to get there with supersolar nitrogen abundances. Okay, so I fully agree about the bias, but even the stream objects are telling us something about how these systems are forming and evolving.
We have time for more questions. Oh, we have three, so let's go 1, 2, and 3 in the back.
I have a question about distinguishing the systems with the absorption that you showed from this lower AGN, because if I look at the line profile, it's not particularly different. And you showed the IFU data as well. I mean, you don't resolve the two components.
Oh, let me. Which lines are you referring to? This one?
No, at the very end when you were showing the H-alpha.
H-alpha absorption could be mimicked by dual AGN.
Ah, no, okay. Is this the very last one? Sorry, is this one? Yeah, okay. So indeed, so this is a BLR which is totally offset. Okay, so in the region, so there is no doubt that this is a separate system. Okay, in this case, this is you have this broad component and this wing here, which in principle can be outflow, can be a peculiar BLR because now against the outflow we don't see this wing in the oxygen tree, so it's not actually an outflow, and could be a weird BLR. Okay, but the interesting thing is that I don't have the figure here, but if when you map this wing and you map the broad component, you see them actually offset. So it's not just the BLR with some clumps in the accretion disk and so on. It's actually two components that are separated indeed by about 200 parsec. So are physically, this is all thanks to the integral field observation where you can actually manage to separate these components. There is a very instructive figure in this paper, 2025, where you can, yeah.
Okay, we do 2 more. So, go.
So the question regarding the mechanism, right? You said that you can use it to grow star formation that starts in the center or starts on the outside of the galaxy. So how does this work in the early universe when most of the objects we have are not actually resolved?
Yeah, no, well, in what I showed actually are, you mean in simulations or in observations? Okay.
How do you measure this? When you cannot resolve
No. In all of those, when we don't resolve, we don't report the gradient. So again, this is a biased view of the gradients. But all of those that I showed are actually resolved systems. So again, with integral field spectroscopy, we resolve these gradients. I mean, the word is, sorry. There are quite a few of these cases where we managed to resolve the gradients. In some cases, even directly. In others, okay, sorry. So this is a clear case where we resolve this, and these other cases, okay. In many of these cases, you use how to say, the strong line method, so that you see the variation of the line ratios, and it's spatially resolved. But there are actually a number of cases where we manage to resolve the directly by using the auroral line. The auroral line is so strong that we can map it and directly observe the gradient. So actually, all of these that I've shown here are actually well resolved. So it's true that are small, but again, JWST is quite powerful.
Last question.
I was wondering if there is any recent reanalysis of all JWST gen, including for electron scattering on the one hand, for the black hole mass, and the Balmer break not being stellar in terms of the stellar mass we have to turn. I mean, what I mean is, these plots that we're seeing are being mainly determined before these effects were.
So yes, this has been done, but there is well, there are various aspects for the exponential, for the profile of the lines. To begin with, only actually a fraction of these agents have exponential profiles. And so let's say 30%, okay? So in those cases, you can argue that this is electron scattering. However, even in those cases, there is no consensus that those exponential wings, one, are exponential, and two, that are due to electron scattering, because there is other works that claim that since the profile, in the electron scattering scenario, all emission lines should have the same profiles, and that doesn't happen in many cases. So this has been debated that is the case. So whether you should correct or not is not obvious. On the other hand, now there are growing efforts in doing this spatially resolved, resolving the sphere of influence with spectroastrometry, and this has been done. And so this actually, I think, is hopefully more robust, especially in those cases where you can do that. Unfortunately, it's doable probably only for a fraction of the agents. And for the stellar masses, yes, in the last work that we did on jades, we, being unsure about the origin of the Balmer break, we essentially developed a completely independent analysis where we relied on the spatially resolved analysis. And the spatially resolved light shouldn't be affected by this nuclear absorption. And the stellar masses that we get there are still putting these objects still there. So in George Bally's, the last work, most of those stellar masses are independent, should be, let's say, more less affected by this issue of the Balmer break. But it's true that. Okay, yeah, when you put together inhomogeneous samples, yeah, it's. There are people who have tried it, but with approaches that I'm not sure are totally solid, even because the data that is available is not as homogeneous. So it's pointless that you try to infer the stellar mass on a galaxy that is very low signal to noise and poorly resolved. So it's, you can do it, but you get probably an answer. But I'm not sure that often the error bars that people are plotting are reasonable. Yeah.